Good morning, all of you. In yesterday's session, we have started about the transient stability, right? So this time starting the session, okay? So the transient stability, okay? Up to the previous session, we have completed about the steady state stability. In the steady session, just we have started about the transient stability. This is a stability, that is, it is the ability of the synchronous machine, which is going to come back to its stable even after the sudden and large disturbance is called as a transient stability. Just I will revise the concept what we have discussed in the yesterday's class. Okay. So to determine the transient stability, we require the swing equation first of all, because anything what you're going to solve to determine the transient stability, the first point what we require is a swing equation. I have already defined what is actually a swing. Swing is nothing but a change in the rotor axis with respect to stator axis is called a swing. This change in rotor axis is due to disturbance condition. Just if there is any disturbance, then the rotor axis is going to get accelerated or decelerated. Therefore, this delta will change. For that reason, we are going to call it as change in the rotor axis. So we can also define. So I will try to zoom here. Okay, we can also define this swing equation as relative motion of the rotor axis with respect to stator axis as a function of a time will give you the swing equation. Nothing but this delta d delta by dt, d delta divided by dt will give you the swing equation. So for that reason, to derive the formula for the swing equation, we took one synchronous generator. We have assumed the shaft torque as well as electrical torque, where the accelerating torque is equal to the shaft torque minus electrical torque. If there is no disturbance condition, that indicates it is under equilibrium condition, right? That is equal to 0. So we have already, we took accelerating power, which is equal to accelerating torque into omega, that is nothing but an angular velocity. And we got accelerating power is equal to m into alpha. So, but what is this alpha? Just we have derived from this equation, that is considering a synchronously rotating axis, which is going to rotate with omega r and time, and stator axis and the rotor axis. Okay, this is actually practical phasor diagram of the synchronous generator. So delta is not exactly an angle difference between the rotor axis and the stator axis, but it is an angle difference between the rotor axis and the synchronously rotating axis. So rotor axis, stator axis angle difference is theta, which you could able to write theta is equal to delta plus omega r into t, because it is going to rotate with respect to omega r speed. So every angle should be in terms of radians. So theta is in terms of radians, delta is in terms of radians, omega r also should be in terms of radians, but it is actually radians per second. For that reason, we have multiplied with time. So after doing the differentiation, we got d theta by dt is equal to d delta by dt plus omega r. And still, if you are doing again the differentiation, you will get d squared theta by dt square is equal to d square delta by dt square. What is this d square theta by dt square? Is nothing but an alpha. Alpha is equal to d square theta by dt square. Okay. So just if you substitute that one, that alpha here, that is d square theta by dt square, which is equal to d square delta by dt square. Therefore, you will get PA is equal to m into d square delta by dt square. This is actually a swing equation. Okay. You see here, d square m into d square delta by dt square is equal to accelerating power, which is equal to shaft power minus electrical power. Okay, this is actually a swing equation. Now we'll try to determine this transient stability. Okay, we need to determine the transient stability. How we are going to determine transient stability? Transient. So we should determine this transient stability. So in order to determine this transient stability, usually we have two methods. Okay, usually we have two methods. The method one is, you're going to call it as a graphical method. Okay. So the method two is numerical method. We have two methods in order to determine the transient stability. Similarly, how we are determine the steady state stability. Okay. Similarly, we are going to determine the numerical method. So what is actually this graphical method? We have only one method under this one. We are going to call it area criteria. This is actually equal area criteria method based on the area we are going to decide either the synchronous generator will come to stable or not. That is, it could able to come to stable or not. We are going to decide based on the area. That is called as an equal area criteria method. So coming to under the numerical method, we have so many number of methods, but the mostly discussed method is a point by point method. Point method. Okay. These are the, according to your syllabus, we have these two methods. Not only the point by point method, we have an Euler's method, we have a modified Euler's method, we have so many number of numerical methods. But compared to the accurate solution, point by point method will give you the accurate solution. Okay. So these are the two methods. One method is a graphical, the one method is a numerical method. In the graphical method, we are going to use only one method called as an equal area criteria method. And under the numerical method, we are going to discuss only one method called as a point by point method. Okay. So this is a point by point method. Okay. So we are going to discuss these two methods under the determination of a transient stability. After this discussion completed about the two methods, we are going to determine the methods to improve the transient stability. Then after this 15 unit will get completed. So, but that is not that much easy because we need to discuss equal area criteria method. We need to discuss also the applications under the equal area criteria method. Then after we need to discuss about the point by point method. Those applications are will be one or approximately 2 to 3 like that. Okay, based on the timings we are going to discuss that one. Now let us try to discuss about equal area criteria method. Okay, let us try to discuss about the equal area criteria method. So first one, equal area criteria method. Equal area. So in order to discuss about this equal area criteria method, first you need to write down the equation of it. That is, you need to bring the equation from the swing. What is actually swing equation? Swing equation, see, this is actually swing equation. See here. This is actually swing equation. If you see perfectly, this md square delta by dt square is equal to pa, which is equal to ps minus p, is a swing equation, right? So just I will discuss here. See here. So in this swing equation, what happens? Just by using this swing equation, we are multiplying the 2d delta by dt on both sides. So when you are multiplying 2d delta by dt on the both sides, if you simplify this one, just have multiplied. See here, integration of 2d delta by dt and md squared delta, d squared delta by dt square into dt, which is equal to integration of 2 ps minus p. I'm not writing pa, that ps minus p into d delta by dt into dt. Okay. So because you are applying the integration also, because it is integration with respect to d delta by dt and also integration with respect to time. So integration to d delta by dt dt to integration d delta by t and the dt, right? Now after simplifying this one, what you're going to get is, this is the formula what you're going to get, that is d delta by dt is equal to root of 2 by m integration of delta naught to delta. Delta naught is the angle when there is no disturbance. Okay, is the angle when after the disturbance is cleared, at which angle it is going to settle, we are going to call that as a delta. Okay. Next, ps minus p, that is ps is the shaft power, p is the electrical output power of the synchronous generator with respect to d delta plus some constant. Okay. So now I will try to draw this d delta by dt. If I want to draw these characteristics, how it will be like this. See. Okay, so just I'm trying to draw delta versus time. Okay, I'm trying to draw the delta versus time. If this is some delta naught, you can assume this is a delta naught. Delta naught is some initial angle when there is no disturbance. So always we are going to use that naught, p naught, delta naught, every naught, because it is under the initial conditions where there is no disturbance. So this is actually at initial conditions. Okay, where it is remain as a constant because I have written in terms of a per unit value. Okay, this is not DC, don't consider this as a DC value. Okay. in terms of per unit value, okay, at time t. You can consider some time t1 like that. Okay, so what happens at this point, the disturbance have been occurred. So when the disturbance have been occurred, what happens, for example, if you take a synchronous generator or any three-phase fault have been occurred, what happens? So suddenly it will try to be oscillated and it will come to its own equilibrium point. Okay, this is the new delta point. Okay, so this is the new delta point. I'm going to call this delta naught as this angle as a delta. You can see here in the equation, delta naught to delta. Delta naught is the initial value, delta is the final value which is going to set it. Okay, this is the delta. That is after, so after when the fault is taking place on a synchronous generator, therefore the rotor will, the angle will be get accelerated. That is, angle will start increasing. So when the angle is increasing, it will not come to the steady state point at the same time. It will do some oscillations and then it will come to steady state point. Clear? So this, what you're going to call this as, this is actually the first swing. Okay, this is the first swing. We are going to name it as first swing. Okay. Please all of you listen carefully, very very important concept. So this is actually first swing. If I want, this is under stable conditions. If I would, if I would like to draw also the characteristics of an, not able to say, for example, if it is a delta naught, if not I will draw with a different color here. Here, after when the fault have been applied, what happens? This is for stable condition. This is actually for unstable condition. Okay, the green color indicates for unstable condition. The red color indicates for stable condition. Here, this is only for stable. This is it. It returned back to the stable operating point. Okay. See, I'm indicating everything for your better understanding. Is actually it is returned to the stable operating point, but whereas it is, this one is, so this green color indicates for an unstable operating point, this red color indicates for stable operating point after the disturbance. Okay, when the disturbance took place. So that means it is moving to unstable. So by seeing the characteristics itself, we could able to find that this value, this green color, which is an unstable, is increasing completely. Okay, but whereas for a stable operating point, in the first swing itself, it is coming back, it is decreasing here. If you see, if you observe clearly, see here, see, after when it is coming, it is not increasing. At one point it started decreasing. When it started decreasing, that indicates at any point it will come to stable operating point. We are going to call it as a first swing. If you see, the magnitude is this one, and the next second swing the magnitude will be get decreased, and third swing the magnitude will be get decreased, and the fourth swing the magnitude will be get decreased, and at one swing it will come to the stable operating point, right? That means you should concentrate mainly on the first swing. You need to do analysis on the first swing, either it is getting stable or not. Okay, so what happened, what is this point is, this point is nothing but an d, what happens here, the change in d delta by dt is actually 0 because there is no change. For that reason we are going to call it as a stable. So for stable operating point, what we need to do, so this d delta by dt is equal to 0. So when this d delta by dt is equal to 0, see here, so this d delta by dt is equal to 0 for a stable operating point. Therefore, if you are substituting 0 in this equation, what you are going to get is integration of delta naught to delta. Only this part will be get remain. Ps minus Pa into d delta is equal to 0. What is this? Ps minus Pa is nothing but an accelerating power. Okay, so that is integration of from initial angle to the new angle. Pa into d delta is 0. What is this? Actually says the area under the curve of accelerating power is equal to 0. The area under the accelerating power is equal to 0. Okay, that is nothing but an equal area criteria. I'm saying that the area under the accelerating power should be equal to 0. then only we are going to call this method as the equal area criteria method. Okay. See, this means that area under the curve PA should be equal to 0. That is, if it should be 0 means it will have two things. Okay, the one thing is PA is the one thing is PA is accelerating as well as a decelerating. So when it will be get accelerated, it will be get accelerated when PA is greater than PE, right? It will be get accelerated when when PS is greater than PA, and it will be get accelerated when PE is greater than PS. I have already shared the notes in your Google Classroom. Giridhar, I have already shared your notes in the Google Classroom. Please open your Google Classroom. Okay, if you are not getting the Google that notes again, you can give me a message. I will send you. Okay, but I will share in the group again. Okay. So these are the two things. Just I will explain this one by considering one example. But here, equal area criteria method, the area under the PA accelerating pole should be equal to 0. That indicates that okay, so that is integration of PA into d delta, okay, should be equal to 0, right? So which actually says that, so we already know PA is equal to PS minus PA, right? PS minus P. So based on this equation only, it will be get, if this is if this is increasing, what happens? It will be get accelerated. Okay, under this condition, if PA increases, accelerating, P is not increasing, if only P is increasing. Okay, P is not increasing, if only P increasing, what happens? It will be get decelerated. So the area under the curve of accelerating and area under the curve of decelerating should be same. If this area is same, then we are going to call the system as a stable. If this area is not same, then we are going to call the system as unstable. Okay, I will take one example. Okay, so just I'm taking one synchronous generator and one curve. So for the better understanding, I'm going to take one example. Okay, it contains with reactance or like that, and you can draw the reactance of a generator. This is and the bus. Okay, this is actually the electrical power which is going to deliver by generator, and the mechanical power which is going to be for the input of the generator. This is the electrical power. I'm writing it as P. Mechanical power or shaft power. Okay, both are same. Shaft power which you are giving to the synchronous generator. Right? So now, if I want to write the characteristics, I think you already know what is this electrical power. Electrical power is equal to excitation voltage, which we have already derived EV by X. This is the equation of electrical power. So now I'm drawing the curve. See clearly. So this is the curve. So we need to draw the curve P versus delta. I have already told which is the relation between the P versus delta. So how the curve should be look like? It should look like a sinusoidal, and we need to take only the first swing. I have already told this is the power, and this is the electrical power. This is PE. Power, which it is equal to EV by X sine delta. And we also have shaft power or a mechanical power, because this is actually, and consider this straight line. It is a straight line, which it is a mechanical power. So now I have drawn these two characteristics. The first characteristic is the shaft power, and the second characteristic. Why the shaft power I have drawn it as a constant? Because it is not possible to change the shaft power within a fraction of a time. For example, if there is any disturbance is going to occur, it is impossible to change the shaft power at that fraction of time. It requires so much of time. It requires so much of time to change this shaft power. Okay. Sorry for the disturbance. Okay, this is actually shaft power which is remained as a constant, and this is the electrical power which it is going to vary with respect to delta, right? So at this condition, if you observe clearly at this condition, what is this condition? This condition is where PS is equal to P, right? This is the condition where PS is equal to P, and I'm going to use this condition as an initial angle, that is delta naught. Okay, if you substitute the delta naught, what is the amount of power you're going to get? That amount of the power is equal to the shaft power, and at that point, what it will happen, that is PA, which is equal to and that will give you equal to 0. This is called as an, there is no disturbance condition. Okay, and there is an angle difference between the rotor axis and the stator axis. That angle difference is nothing but an delta naught. That angle difference is nothing but a delta naught, and at this point the PS is equal to P. Okay, there is no disturbance at this point. Okay, now we'll try to, the system is running perfectly until this condition. Now what happens? Suddenly a three-phase fault have been taken place. Okay, a severe fault have been taken place. I'm assuming the fault as a three-phase fault. So when the severe fault have been taken place, what happens to the electrical power? Electrical power will drop to 0. When the three-phase fault have been taken place, the electrical power, what it is going to deliver, electrical power is what the synchronous generator is going to deliver to the transmission lines or the computer system, will drop to 0. Right? So when it is dropping to 0, what happens at this condition? The power which it is going to transmit will come to 0, because electrical power will come to 0, but PS is not going to do anything. It will not change. See, it is a constant. So now a fault has been taken place. So due to that fault, electrical power is now 0. So when this electrical power is 0, which makes the electrical power, electrical output of a generator is a 0. Okay, because there is no load to supply. So after some time, the fault is cleared. Okay, after some time, you can assume this time and delta 1. Okay, so when the fault is taken place, what happens? The rotor axis, because electrical power is equal to 0, there is no load, then the rotor will start accelerating, because if there is no load, what happens? The rotor will start accelerating. When it is starting accelerating, this is a stator axis and this is a rotor axis. Okay, and this is a delta. Okay, and what happens? The rotor accelerating means it will be get acceleration, then delta will start increasing. That is, now this is the new point. This is the new point of rotor axis. Now this is the new delta. Okay, that is, delta will increase because the rotor is accelerated. So the delta increases to delta 1, but still there is no electrical output power. But at delta 1, now what happens? The fault has been cleared. At delta 1, the fault has been cleared. Then what happens? It will try to move to the point of P. Okay, because it is not going to stop at the point. It will move to the point of P. Okay, this is the point. Okay, so at this point, what is the condition? If you clearly observe at this point, what happens? The PE is not equal to PS, but it is greater than PS, right? Okay, at PE it is greater than PS. P, the electrical output power is greater than the shaft power at this condition. Okay, at this condition, therefore, it will start accelerating. See here, what happens? P is greater than PS. What happens? It will start decelerating. Sorry. See here, now here PS minus PE. Now PE is more than the PS, so that you will get negative value. When you're getting the negative value, what happens? It will start decelerating. It will start decelerating. That means it will still increase. Okay. And at one point of time, what happens? It will come back to it's this point, and again it is achieving the PS is equal to P. Again it is achieving the PS is equal to P. That is stable operating point. So at which point it is occurring? At this point, and we are going to call this as again another angle delta. If not, you can call it as a delta maximum. Okay. See, we have two conditions. You have also another condition here. You can see here. What is this condition here? In this condition, S is greater than. In this condition, PS is greater than P. In this condition, PS is greater than P. Okay. And this is actually area. We are going to call this area as A1. Okay. And we are going to call this area as A2. So this is actually when A1 is equal to A2. When A1, give me 1 minute. Now at this point what happens? Now this is an A1 is equal to A2. For example, if this area A1 is equal to A2, then we are going to consider this system as a stable condition. We are going to consider this system as stable. Okay. We are going to call this as an equal area criteria method because area is equal. For that reason, we are going to call it as an equal area criteria method. If A1 is not equal to A2, if A1 is not equal to A2, then what happens? If A1 is not equal to A2, therefore we are going to call the system as unstable operation. Yeah. So I have already told we have an accelerating area and a decelerating area. Accelerating area is this one, decelerating area is this one. So accelerating area is going to take place when PS is greater than PA, and decelerating area is going to take place when P is greater than PS. Clear? So the important thing in this one is I'm telling again this concept. You can see here. So at point delta naught, okay, at a point delta naught, okay, we have 10 minutes on the left. At point delta naught, PS is equal to P. I'm writing here again. At this point, PS is equal to P. Right? So at this point, so now what happens suddenly? Fault has been taken place. A three-phase fault has been taken place on the synchronous generator. Therefore, the electrical power what it could able to deliver will be equal to 0. Therefore, the electrical power is going to drop. See, till this for this complete concept, PS is remained constant only. If you observe, PS is remained constant. Okay, the PA should need to be is trying to be equal to PS. P always is trying to be equal to PS. Clear? Clear. So now what happens? So at delta naught, it comes to the angle of delta naught. This is actually the PE position. This is the PS position. Now in this case, PS is greater than P. So it will be get accelerated. That is, the rotor will also get accelerated. So when it is going to get accelerated, it comes to the point of delta 1. So assuming at this delta 1, okay, at this delta 1, what happens? The fault have been cleared. Just assume that fault have been cleared. So when the fault have been cleared, what happens? It will try to move to the P. Okay, this is the sinusoidal curve of P here, right? That is, if you are substituting this delta 1 in this formula, you will get one value. That value is this one. But at this position, what happens? PA is greater than PS. That is, electrical power is more than compared to the shaft power. Therefore, that indicates a negative. That indicates negative means it will start decelerating. So decelerating means it will move to this position. And at one point of time, it will move to this one. At what is this point of time? We are going to call this a delta maximum value. Okay. So if you apply the same, therefore what happens? This accelerating area is equal to decelerating area. Then if these two areas are equal, then we are going to call this a system as a stable. If these two areas are unequal, then we are going to call this an unstable, and we are going to call this as a graphical method. Okay. And we could also able to define this one as, for example, so whenever the fault have been taken place, the rotor is accelerating. Okay, the rotor is accelerating. That means it will try to store the kinetic energy in that one, because there is no load. We have not removed the shaft power, and there is no load. Okay? We have not removed any shaft power. But there is no load. But P is equal to 0. Therefore, this rotor is going to store that kinetic energy. Okay, that kinetic energy, what it is stored, will be given up at this place. Okay, at this decelerating area, whatever the kinetic energy is stored, okay, that will be given up here. The kinetic energy, all the kinetic energy, what it will be stored, will be given here. Therefore, PS will come to this point, which is equal to PE. Sorry, P will come to this point, which is equal to PS. Okay, so therefore, that indicates that if you, after coming to this point, you should need to compare the areas. You should not decide the system is a stable. You need to compare the areas A1 and A2. Those two are same, then we are going to call a system as a stable. If these two areas are not same, then we are going to call it as unstable. So when we are going to call as an unstable, I will give you an idea. So see here, this is actually delta 1. So where at this delta 1, the electrical power is coming into the picture, which is going to greater than PS. For example, here the fault has been not cleared. Just assume that the fault has been not cleared at this point. Is this right? When the fault is cleared, only the electrical power will come into picture. But now the fault has not cleared. The fault has been cleared at some where here. The fault has been cleared at very long away from this delta 1, means what happens? The accelerating area will be so much high, or the rotor which it is going to store the energy will be so much high, and there will be no place. This time I will draw with another color. See here, if this is a delta 1, what happens? It will come to this point, and this much energy will be stored in the rotor, and there will be it should need to get decelerated, no? But if you compare this one, it will not come to this point. Okay, if you compare these two areas will be unequal and will run into unstable operation. Why? Because of you have the engineer not, or the fault is not cleared at that time. Okay, the fault is cleared very lately. If the fault duration is also more, if the fault clearing time is also more, then what happens? Automatically the synchronous machine will operate under the unstable operation. So this is the equal area criteria method, which it is able to operate stable or unstable, which it decides on the fault clear. So at which time you are going to clear the fault, and with respect to that time only, it is the synchronous generator is able to operate either a stable or unstable operation. Okay, that decides the fault clearing time. Okay. So if the fault clearing time is more, automatically the synchronous generator will lose its synchronism. Unstable operation means it is going to lose its synchronism. Okay. This is actually about the equal area criteria method. The same thing is explained here, but I have drawn in a different curve. You see here, area A1 and area A2. Okay. In this area A1, what happens? The PS is greater than PE. In area A2, P is greater than PS. Okay. In this case, PS is greater than P. In this case, P is greater than PS. Therefore, if these two areas are equal, then we are going to call this as equal area criteria method. See, and also I have considered this point. Area A1 represents the kinetic energy stored by the rotor during the acceleration, right? That is the same thing. This area, and area A2 represents the kinetic energy given up by the rotor to the system when it is decelerating. Therefore, it will come to its original speed. Original speed means it will come to the stable operating point. So in the tomorrow's hour, we'll try to discuss about the applications of area criteria, then after the point by point method. So you can ask me whatever you have doubts. We have left only with 3 minutes. 239. 219. Rule number 219, not connected to audio. See, from tomorrow, I will try to enable the waiting room, because after 9:35 or 9:40, I will enable the waiting room so that I will not admit anyone into the class. Okay, please come before 9:30 to 9:35. Okay. Please, if you have any doubt, ask me. I will clear your doubt here itself. So in the today's session, we have discussed about the equal area criteria method, and we have two methods. One is a graphical method to determine the transient stability. We have two methods. One is a graphical method and another one is a numerical method. Graphical method is a equal area criteria method, which it is nothing but an area under the curve of accelerating power, and another method is a point by point method. In case of steady state, if PS is equal to P, it is in equilibrium, but in transient state, it is in stable. What is the difference? See, in the case of steady state, if PS is equal to P, it is in equilibrium. Equilibrium condition means under no disturbance condition. See, both are, if it is coming the stable condition or also equilibrium condition, both are same. There is no difference. Why we are going to call it as equilibrium? Equilibrium is a new condition. Equilibrium state or steady state, both are same. There is no difference between. But PS is equal to PE is, for example, if there is no fault, then we are going to call it as an equilibrium condition, right? How could you able to differentiate after the fault or before the fault? For that reason, I'm using before the fault as an equilibrium condition, where PS is equal to PE, therefore it is equal to 0. So after the fault, and after the fault have been cleared also, it is coming to the stable operating point again. That indicates again the equilibrium condition, right? Both are same. See, that point indicates that it is operating under the stable condition. Okay, there is no unstable, stable. Is it clear, Chakri? Both are same. Okay, that is a stable, this is also stable. But this is, we are going to call it as a transient stable. Why we are going to call it as a transient stable? Because after a few transients, it is coming to the stable operating point. Anyway, the point is same. Okay. And any more doubts? Okay, so in the tomorrow session, we'll try to discuss about the application. Please try to revise all the concepts what we have discussed in these online classes. Okay, starting from the current limiting reactors of the 4th unit to up to this point. Okay.